Okay, let's get started. Here we go. Okay, a couple announcements. So, you just hold on to him. I can give him one. And in the back, on the right. Okay, so the web work, I have extended it and doubled all your attempts. Come on, where are the rest of you? So it's due tonight at midnight. So I extended it to tonight at midnight. I think what we do in class today will definitely help fill in the gaps if you things you had questions about. So today's class will help, and then whatever number of attempts you had before, I just doubled them. So if it was a 5 question, now it's up to 10 attempts. If it was 2 attempts, you have 4 now. Okay, additional. So you just if you had 2 before and you've used them both, now you have 2 more. Okay. So in addition to new homework that's due Thursday. Okay, so this is an extension until tonight, and then there'll also be homework Thursday. Next announcement is the mastery. So if you go into the grade book, there's a column called Mastery 1. If you have a 0, that means you did not pass on the first attempt. Second attempt, Thursday night, same drill, same place, same time. 6:15, you can arrive anytime from 6:15 to 7:30. And you need to take it, you need to pass it. So you need to get caught up with practice, get into office hours, figure out what you missed, what you still are deficient with the mastery exam. If you have 100, that means you passed. You got your 90% and you get 100 in the grade book. Okay? Any questions about the mastery? Okay, and then finally, our normal TAs have prior engagements unrelated, but they just both happen to not be here today, and so Erica is going to be helping out. She's certified calculus genius, so she's going to be helping you. So she's all right. Okay. Are we ready to start? This is not the right place to start. Okay, let's get started. Okay, ready to start. Here we go. No more talking, please. Can I have your attention? Here we go. So what you worked on with the homework, hopefully you saw that this main idea, this very central idea, was maybe 75 to 80% of it really relates back to really understanding this main idea, that if a function is increasing, what do we know about its rate of change? You should all immediately know that that means the rate of change is positive. Okay? We looked at a little proof of this, right? The rate, if the output of if y is increasing, then how does y final compare to y initial for a little change in x? For a change in x, how does y final compare to y initial if you're increasing? Ian, how does y final compare to y initial if y is increasing? Yeah, y final will be larger. And so then dy will be what? If the final y is greater than the initial y from increasing, then that means the change in y is positive, and then k will be positive. That's why we get the rate of change is positive. So that's like a little proof. So that's a nice little proof that you're responsible for the next exam. Okay? And then similarly, if a function is decreasing, its rate of change is, and they all said together, negative, right? Well, together, I said. All right, and so the proof of this starts with the fact that if it's decreasing, then how does y final compare to y initial? Where's Sierra? Cats. Sierra. If a function is decreasing, how does y for a change in x? How does y final compare to y initial? It's smaller, and so then the change in y is? What's that? No, it's negative, right? So if y is decreasing, that means the final y is less than initial y. It means the change in y is less than 0. and then that's how we get that the rate of change is negative. So really, this web work that you just did, like I said, like 75 to 80% of it really comes down to this fact, just applying this fact in different scenarios, okay? All right, and then we see that these basic principles hold true for any function and its derivative. So the amount function and the rate of change function. But it also holds true for, if you think of your initial function as the derivative, then the derivative of that, or the rate of change of that, is the second derivative. And this same principle holds true. Okay, and then for the second derivative being positive, okay, if the second derivative is positive over to the left, that means that the first derivative is increasing. And then, so now the function then, an increasing first derivative means the function, what, turns counterclockwise, or is concave up, the original function. Okay? Similarly, if your second derivative is negative, that means that the first derivative is decreasing. And if the first derivative is decreasing, that means it's getting less positive or more negative. So it turns down or turns clockwise, turning down. Okay? So that's a review. That's just an overall review. This is kind of the basics of what we're talking about. So we started talking about critical values. A critical value of a function is any value of x where two things could be true. The function exists, and also the first derivative is 0, the rate of change is 0, or the rate of change does not exist. Okay, that's called a critical value. The value of x such that you do get a valid value of the function, and that the first derivative is either 0 or does not exist. These are what we call critical values of the function. And so what does it mean if the first derivative is 0? That means that for a moment, there's a pause, right? The function is not changing. The value of the function is not changing. So there's a pause in the values of the dependent variable of f. So it either stops increasing or decreasing for a moment. And we call that a pause. So this handout that we're about to go through is the different situations for which f prime of c is 0, okay? The different situations that you have for a critical value such that the first derivative is 0, that you have a pause. And the first one is the local max. The local max. And so for each of these, we're gonna view each of these through the lens of the original function, and we're gonna view it through the lens of the first derivative, and we're gonna view it through the lens of the second derivative. So a local max. First, looking at the function itself. Looking at the function itself, we said that a local max really is comprised of there's 3 parts to it that make up, if you're looking at it through the lens of just the original function. All right, and what are the 3 parts that we talked about? Where is Beihan Chen here? Yeah. So we said that if you're talking about a local max, just in light of the function itself, it really comes down to kind of 3 things. Do you remember what it is? So we can see that by looking at this arrow. Looking at this arrow, because this arrow represents the function values as we transpire through a local max. So what does that arrow do? Yep, so at first it increases, and then at the max, what does it do? We got the pause, right? See, pause, and then decrease. Okay, so looking at the function itself, a local max, what's the profile for a local max? We have increasing, and then we have a pause, and then we have decreasing. So that's viewing a local max through the lens of original function. So now we're going to apply the stuff we know about The relationship of a function and its rate of change. So if you have increasing function, then what does that mean about the rate of change? If you have an increasing function, what does that mean about the rate of change? So that's prior to C, right? Prior to C. What can we say about the rate of change? Where's Naomi? Where's Naomi? Not here? How about Jaslyn? German. Jaslyn. Yeah. So we're talking about this first part here, where the function increases. What can we conclude about the rate of change? Positive. Yeah. All right. And then where we have the pause, what can we say about the rate of change? 0. And then where that function is decreasing? Negative. Okay. So now you can sketch what the rate of change will be like in the local area of a local max, because you know it's got to be positive and then 0, then negative. So you make a sketch of that. Make a sketch of that. So where's Yash? Yash. So tell me, if I wanted to sketch a graph that's positive and then 0 and then negative, how would I draw that? Can you sketch it with your finger or explain it to me? So over here, where should I draw it? Above? Okay. Where do I go through the x-axis? At the C point. Okay, so you're saying it's going to be up here like this? And then it's going to go through there? And then what? If the rate of change now is negative over here. Go up? Keep going down. Something like that. So it might be a straight line, it might be one nice curve, we don't know. Okay, so all we know is that around that it's going to be positive and then 0 and then negative for the rate of change. Okay, so now looking at that, what general conclusion can we make about the whole profile for the rate of change for a local max? So if you looked at that as a whole, could you say anything that's true about that as a whole for the rate of change? Adrian, what can you say? Negative everywhere? Decrease. That's different, right? That's different. So it's positive, 0, and negative, but it's decreasing the whole way. You see that? That whole thing is decreasing. Okay, so now if my first derivative is decreasing, what does that mean about the second derivative? Moving over here to the second derivative now. If that whole thing's decreasing, then what about the second derivative? Where's Jacob? Jankowski. Jacob here? Okay. You have a long name that starts with N? Is that? Yeah, okay, I can't pronounce it, I'm sorry. What do you go by? Zoe? Zoe, okay, so Zoe. I've got a function that's decreasing. What can you say about its derivative then? It's negative, right? So how would we sketch that? So now we're viewing a local max through the profile of a second derivative. We know the first derivative is always decreasing. So then what would the second derivative be? And how would you, so sketch the graph. Sketch the graph. How would I sketch that? It's always down here like this. So this is the profile for a local max. If you look at the function, you know it's going to increase, pause, decrease. If you're looking at it through the lens of the first derivative, it's going to be positive, 0, negative, and it's going to decrease through there. It's going to decrease through that local max. And since it decreases, then the second derivative would be always negative around the local max. How does that then relate back to, how does this, the fact the second derivative is negative, relate back to the fact that you have a local max? what's the relationship now? We got a second derivative negative relating back to the original function. How do you see that those agree? Concave down, right? So if the second derivative is negative, it's concave down. That's exactly what happens at a local max. It's concave down. All right. Is the second derivative 0 here? The second derivative, is it 0 at the max? No. What is it? It's negative. It's not 0. That's a really common mistake students think. The first derivative, yes, is 0 because you have a pause. But the second derivative is not 0. You see that it's what? The rate of change is decreasing all the way through here, even at the top. It's still decreasing. It's changing from less positive to becoming more negative. So the second derivative is not 0 there. It's negative at the very top. In fact, it's negative the whole way. Okay, so now that's the example of local max. So you're going to be looking at local min. And I got the animation for you. So first start by saying, okay, what will the profile of the local min be just looking at the function? Then what will it be looking at the rate of change? And then what will it be looking at the second derivative? And so do this. Try not to look at the first one doing it. Don't just go up to the first one and like just make conclusions based on what we did before. Cover it up. Cover up the first one. Start again like you can't see that. And try to do it without looking at what we did in the first row. And work together. Okay, where's Chao Zhang? Where's Chao? Chao Zhang. Yeah, so looking at it through the function, what did you say characterized a local min? So how would you talk about just in the lens of the function, looking at the function, what characterizes a local min? He said decreasing, pause, and increasing. Agree? Yeah, decreasing, pause, increasing. That's how you talk about it in the context of the original function. Okay, what about in the context of the rate of change? Where is Pingyang? You. Pingyang, you. Are you here? All right, Jason. Jason. How would you talk about a local min in the context of the rate of change? Okay, from negative to positive. Anything else? Okay, right. Okay, so the key is that at the minimum, what is the rate of change at the minimum? That's the key that you left out. So it's going to be negative, and then the rate at the pause or at the minimum will be 0, and then the rate will be positive. And so then what will that graph look like? What will that graph look like? Yeah, it'll be going up.
So annoying.
So what's the overall? So then we can make an overall conclusion around a local min. What is the overall conclusion about the local min? Where is Mei Chen? Is Mei here? How about Zhang Mao? Okay, where's Jacob? Espacher. Jacob. Perda, you're up. So when you look at that whole thing, I don't know if you're ready yet, but when you look at that whole, this graph right here, what overall can you say about that rate of change graph?
Well, first of all, the rate of change.
Just one word. So is there one word that characterizes this whole thing? Increasing. 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 And so if a function is increasing, what can we say about its derivative? So now looking at the second derivative, the function is increasing. Positive. Or up here. Okay? Any questions on this? So yeah, drawing the graphs may seem easy, but you know how the web work went, right? So you've got all these questions coming at you about the function and the first derivative and the second derivative, and you're trying to coordinate all at once. And so this is the kind of reasoning. This is the kind of reasoning you have to have. You think about add a local max. What does it look like through the lens of the function, through the lens of the first derivative, through the lens of the second derivative? Okay, so if the first derivative is 0, if you have a critical point, the first derivative is 0, is a max or min guaranteed? Is a max or min guaranteed? Okay, there's something else that can happen, and you saw some in the web work. And so it's what I'm going to call a rest stop. So when you're driving on a road trip and you're on the highway, and there's, it says rest stop 1 mile ahead. And so you pull over to the rest stop, and then you do your business, you get your popcorn, and stretch your legs. And then do you turn around and go home? No, what do you do? At a rest stop, the only option is to do what? After. You have to keep going on the highway. You can only get off and then get back on this, and going in the same direction. This is the idea of a rest stop. Okay? This is the idea of a rest stop. Okay? The only difference between my analogy is that this is like a momentary rest stop. So it's kind of like you pull in and then the car just pauses for 1 moment. Open the door quick, close it, and then yeah, a really, really fast drive-through. Like that they throw the food at you, okay? Okay, so instead of having the arrows, you're going to do it with your fingers. All right, so your right finger is going to be the x-axis, like this, the arrow like this, and your left finger is going to be this arrow, and you're going to recreate it based on that graph. Okay? So your right finger is going to be the x-axis arrow, and that's just going to start at 0 and just increase steadily like this. And then you're going to coordinate your left arrow to match this profile, which we call rest stop 1. Okay? And then you're going to do the same thing again. You're going to talk about this rest stop type 1 in terms of the function, the rate of change, and the second derivative. There's more involved here. This is more complicated. So you have to take from what we learned before, but you have to really think a little harder on these. So give it a shot. I'm just going to leave it all up to you. In a couple minutes, we'll walk around and help you. Okay? Question? Is that a question? Oh. It's not really what we're working on right now. We're just working on if you have a function that has this pause like this, So then we're just talking about increasing, decreasing, positive, negative, 0 for these different functions. But you're right, it would have to be a cubic or higher degree. Yeah, so reason it out. Reason it out. Increasing, decreasing on the graphs. That's what this is about, not just can I get the graph right. Do you understand what's increasing, what's negative, what's positive? That's going to be your understanding of this. Not that I can just sketch a graph fast. Okay, so label all that stuff. Increasing, decreasing, positive, negative, 0. For all these parts. Okay, Laura, you're up. Let's regroup. Here we go. How about the original function? Tell me about a rest stop type 1. What's the profile in the original function? Yeah.
Okay, so what I think that I got was the first part is like decreasing, and then the second, or then it pauses, and then it starts increasing.
So it's decreasing, pause, and increasing.
Yes.
Didn't we already do that for a different kind of critical value? What's that? Decreasing, pause, increasing. That's a local min, right?
Increasing, pause, increasing.
Yeah, so it's increasing, like you're going down the highway, right? You pause and you keep going down the highway at a rest stop, right? So increasing, pause, increasing. That's what it looks like through the eyes of the function. Okay, so what about for the first derivative? All right, where's Megan? Thomas? Megan. So what can we say then about the first derivative if we've got increasing, pause, increasing?
It's positive, and then it becomes 0, and then it's positive.
So what would that graph of that first derivative look like?
Above the
So if it's above, so just like this? Just above like this up here? But what did you say? You said what? Positive and then?
okay. So it has to go down to the x-axis and then go back up.
Right. So it's going to be, it'll be positive, but it's going to be 0 there, right? We got a pause. A pause means the first derivative is 0, and then positive again. So like she said, it's going to have to do this. Come down like this, 0, and then up like that. And that's not a point, right? It'll be smooth. Like that, something like that. Okay, so then if we wanted to talk about the second derivative, then we need to talk about increasing and decreasing. So how does the first derivative now, how do we frame it in terms of increasing and decreasing to make the jump to second derivative? Some of you are saying it. So first it does what? Decreasing, and then pause, and then increasing. So then what about the second derivative? Negative, 0, positive. So what will that look like? How would that graph be done? Everyone draw it with your finger. Yeah, so it's going to be down below, and then 0, and then like this. Which means it's always... no, not always positive. What's happening there? Increasing. So these rest stops are more complicated. Okay, so do rest stop type 2. Go. Take notes about positive, negative, increasing, decreasing. Cover up what you just did. Start from scratch. Don't use this one as an example to copy and just change everything. Cover this up. Do it from scratch. All right, where's Bo? Bo Wan. Bo here? Nope. How about Yi? You. Is Yi here? Ori. You're up. Tell me about a rest stop type 2. What's the original function like? He said decrease, pause, decrease. Agree? That's right. So Ori, keep going. Then what about the first derivative? If we decrease and then pause and then decrease, our first derivative would be negative. So what is the first derivative at C? So this is the theme of the whole conversation. What is the first derivative at C? This is the whole this is where we all started from, right? 0. That's the whole point of all this whole worksheet you're doing. It's where you get a momentary pause where the first derivative is 0. It's a critical value. So you're going to have, say it again now. Okay, so a negative function means the first derivative is, sorry, decreasing function means the first derivative is negative. So it's going to be negative, 0, and then negative. So what does the graph of that look like? Below the x-axis, but when I get to C, I've got to get to 0. So that means it has to look like this. Something like that. So what's the profile for that? What? Increasing, then pause, then decreasing. Which means the second derivative? No, it doesn't mean the second derivative is decreasing. Positive, 0, negative. And what does that look? Draw it with your finger. Overall conclusion about the second derivative. Decreasing. Okay, so these are the four that sheet you just finished is the 4 different possibilities for when the first derivative is 0. What we call critical values. Critical values when the first derivative is 0. Local min, local max, or the 2 rest stops. Okay, no question.
Yeah, isn't it also critical value when the derivative is undefined?
You read my mind.
Yeah.
Critical values where the first derivative does not exist. And so what situations do we have there? We've seen it before. So where is it that at a moment the first derivative would not exist, but the function does? So the first is what? It's a corner point. Corner point. And the second one is vertical at a point. So here's the example. So the corner point would be the example would be the graph that's red. We've done it before. No matter how far you zoom in, such that value of the corner point is in your range. No matter how far you zoom in, you can never make it look linear. There will always be a corner point. So you don't have rate of change at that moment of the corner point. So it's undefined. Similarly with the vertical, no matter how far you zoom in this case at x equals 1, as you keep zooming in further and further, your rate of change will just keep getting greater and greater and greater with no limit. So it's vertical, so you don't really hone in on a particular rate of change. It just keeps flying off to infinity as you make the change in x smaller and smaller and smaller around that point. So for both these cases, the first derivative does not exist. So these are also critical points. So we just want to mention that, okay? So let's do an example here where we have to kind of put lots of things together here. Any questions on these types of critical values? All right. So here's a function, j of x. We want to find all critical values and values for which the second derivative is 0. Okay, those aren't called critical values, but those are also important. Critical values are just specifically values of x that make the first derivative 0. And then we want to qualify each of these through an analysis of j, j prime, and j double prime, like you spent doing on your activity, your worksheet. So if we want to know critical values, we've got this function. So now it's like the whole purpose of the activity was to get kind of a mental, visual image of all these things, because when you come to a problem like this, we're going to approach it algebraically. So then you have to bring those mental images to a problem like this that it's going to be all symbols and equations. Okay, so if we want critical values, then what are we going to need first? Yeah, so we want the values of x that make the derivative 0. So we need the derivative, right? So do it up here. So the derivative is?
Negative 15 plus 18x.
And so now, after the mastery test, we die for derivatives like this, right? So derivative is negative 15 plus?
Plus 18x minus 3x.
Okay, and so we want to know where values of x that make it 0. So what we're saying is we're going to have, so negative 3x squared, I'm going to put it in decreasing order of degree here, plus 18x minus 15. We want to know x values that make it 0, and those will be our critical values. Or undefined, right? Or undefined. So we can simplify this first. Since it's equal to 0, we can divide both sides by negative 3, and we get x squared minus 6x plus 5. And then hopefully this is an easy one.
X minus 5 minus 1. Yeah, x minus 5 minus 1.
So x minus 5 and x minus 1. Remember factoring quadratics to find the zeros. So we got zeros at, therefore, x equals 1 and 5. Are there any values of x that make the first derivative undefined? So we also have that possibility. Are there any values of x that make the derivative undefined? The answer is no. It's just a polynomial. All values of x are valid. So the only critical values we have are the x's that make that first derivative 0. Okay, so let's look at x equals 1. So we may have a local min, a local max, or one of the two types of rest stops at x equals 1. We don't know. So let's look at it through the lens of j. So looking at this through the lens of j, what do we need? We want to find what is the value of the function a little bit to the left of 1, at 1, and a little bit to the right of 1, and then we can conclude what's happening before and after, and we can kind of decide which one it is. So for j, we could look at, say, j of 0. Look at j of at 1. And then look at j of, say, 2. So this is looking at this critical value at x equals 1 through the lens of j. And so what is j of 0? It looks easy. 2. What's j of 1? 11 minus 16, I think it's negative 5. Check my math. I got 9, 11, and minus 16. I think that's right. And then j of 2. Minus 38 and plus 38. Is that 0? Did I do the math right? Check my work. So what do we have? We've got 2, and then -5, and then 0. So based on looking just at J, what would you conclude about what kind of critical value do we have at x equals 1? So it's 2, and then -5, and then 0. Which of the 4 types of, what do we have? You should be saying local min. Why? Because a local min, we have decreasing, and then a pause, and then increasing. So that means we'd have higher values of the function on either side of the critical value. Yeah. Sure, because for x increasing x, right? Yeah. What's that? But the point is, so that at that local minimum, the value is -5, right? So the y value is -5 down here. So if you're to the left of it, you're higher, and if you're to the right of it, you're higher up at 0. So that's local min. Is that better? Okay. So now, what about through the lens of J inverse? Okay, so what did we say what did you say for a local min? What happens with not J inverse, the derivative, first derivative. What's true about the profile of a local min in terms of, or in the context of, the first derivative? What do we have? So what would it be? To the left of it, it would be negative, and then we already know it's 0 because that's where we got the x equals 1. And then to the right of it, positive, right? So we could look at the first derivative at 0. And what is the first derivative? What's the value of the first derivative at 0? -15. And then what's the value of the first derivative at 2? So we'd have 36 minus 12 minus 15. Is that 9? Check my math. So just to the left of our critical value, we have a negative first derivative, and then to the right, we have a positive first derivative. What does that suggest? Local max? So this is what I mean about like taking notes about the min, the max, the decreasing and increasing. So now it's kind of where like we have this information and we have to remember back to that activity that we did. So if the first derivative is negative, that means that the function is doing what? Decreasing, right? Decreasing. And then the first derivative is positive, the original function is increasing. It better suggest the same thing or we're in trouble, right? So we're just looking at it through the 3 different lenses. Finally, for a local min, what about the second derivative? What should be true about a local min, the second derivative? So what's happening to the rate of change? What's happening to the rate of change? Around at the bottom of a local min. The rate of change is increasing, becoming less negative, more positive. So second derivative should be, the first derivative is increasing, second derivative should be positive. So we can do the second derivative at the point in question, and we should get a positive value to confirm it's a local min. So if we plug it in here, we get -15 No, second derivative. We didn't take it yet. So what is the second derivative? 18 minus 6x. Plug in 1, we get 12. Greater than 0. Means rate of change is increasing. Again, local min. Local min. Okay, you practice, so you're going to do the other one. X equals 5. So for x equals 5, analyze it in the context of the original function j, the first derivative, and the second derivative. And you should get the same conclusion on all three. You should get the same conclusion on all three. Anybody have a question about what I did? So this relates, it's relating back to what we did with the graphs, but without the graphs. So it's the graphs, you have to have that visual image without having the graph. So we're relating that back to the graphs that we did without having the graphs. Okay, so you do x equals 5. Let's just do first and second derivative. Let's just do first and second derivative, since that'll take too much time to put those values in. So just do it in terms of the first derivative and the second derivative to save time. Okay, question. So I didn't know when I started doing it. Either side of one, so it's 0 and 2. So then I saw that y value is 2 and negative 5 got there's 0. So there's y value negative 5. For the first one, we already have so we want to see that Did anyone find j prime of 4? What'd you get? 9. J prime of 6. Negative 15. So by looking at the first derivative a little bit to the left, a little bit to the right of x equals 5, it gives us an indication of what's happening with the function. So looking at the first derivative at 4, we got 9. What does that tell us about j? That's positive. That first derivative is positive. It tells us that j is increasing. We know that the first derivative is 0 at 5, so increasing, and then we got to pause at 5. And then what does the fact that the first derivative is negative to the right of 5, or at 6, mean? Decreasing. So we've got, yeah, so this is showing increasing because 9 is greater than 0. And then we know we got to pause at x equals 5 because that was a critical value. And then to the right, first derivative is negative, meaning that the function is decreasing. So the first derivative is indicating what? Local max. Does it make sense? And if we have a local max, then what should the second derivative be? Local max, what's happening to the rate? Decreasing, right? Becoming less positive, more negative. Even at the top, the rate of change is decreasing, even at the top. Therefore, the second derivative should be negative, and it is, negative 12. Again, that's also confirming local max. Okay, so we're doing all the same stuff that you did on that sheet, now without the graphs. So you're mentally envisioning the graph through the numbers, through like a numerical analysis of it. Anybody have a question? So that's the critical values. Yes, please. To get the critical values. So, yeah, yes, where critical values are values of x that make the first derivative 0. So we got to find those x values first. So I took the first derivative and set it equal to 0, solved for 1 and 5. And so the first thing I did was, I did the whole analysis on x equals 1, but knowing that f prime of 1 is 0, critical value, right? And then you guys just did x equals 5, again, f prime of 5 is 0. It's a critical value. So we're trying to figure out which of the 4 it is. So for x equals 1, which of the 4 is it? It turned out to be local min. For x equals 5, which of the 4 was it? It turned out to be local max. Yeah?
Why didn't we do the original
just to kind of practice our understanding of what does a local min look like just through if we frame it in terms of the function. A local min it'll be higher on the left, and it'll hit the low point, and it'll be higher on the right. And so that's exactly what happened. It's higher y value on the left, and then our low point's negative 5, and then it's up higher again on the right. So it's just like we looked at the activity, we looked at critical values kind of through the perspective of each. We're doing it also now like algebraically and numerically here. So if you just wanted to figure out that it was a local min, you don't have to do all three. We're just practicing our understanding. You don't have to do all three. Really, so like for the second one, all you would need is that the second derivative is negative, and that's local max. Because that's the only one of the 4 cases where the second derivative is negative of the 4 cases of a critical value. So then that would be enough to conclude local max. We're just practicing it through each perspective. Other question? Yeah.
So instead of setting the original equation equal to 0, you set the first derivative equal to 0 through the rate of change to 0, right?
Critical values are when the rate of change is 0, where we have a pause in the function, right?
That's why you determine the whole thing.
And that was the 4 different cases that we went through in the activity. The 4 different pauses are increase, pause, decrease. Decrease, pause, increase. Increase, pause, increase. Decrease, pause, decrease. Those are the 4 possibilities. So we went through all 4 of them. What would we be getting if we set the original function equal to 0? Then what would, just the roots, right? The x-intercepts of the graph. If you set that original function equal to 0, just be where that graph crosses the x-axis. If the first derivative is equal to 0, that's where you're going to get a momentary pause in the y value. Or constant, no change, right? No change for a moment. Okay, what does if the second derivative, so any more questions on analyzing the critical values? So we also want to look at where the second derivative equals 0. That's not a critical value, but that's an important thing. So what was our second derivative again? So first derivative, let's do it again here. Minus 15. (18 minus 6x). Okay, so what about the second derivative being equal to 0? So that's saying 18 minus 6x equals 0, which means x equals 3. What is the first derivative at 3? So if we took the first, is it 0? Negative 15 plus 54 minus 27. Is that 12? Check my math. I think that's right. Is that right? Okay, so what does it mean that the first derivative, let's talk about the first derivative first. The first derivative is 12. What does that mean for the function? What does that mean for j? If the first derivative is 12. Where's Brandon Chavez? Okay, Brandon, tell me. We got positive 12 for the first derivative, so the function is? Increasing, right? We got a positive first derivative, increasing. So then it's increasing, but then the second derivative is 0. And at 1 we had local min, is that right? And at 5 we had local max. Is that right? So at 3, does it pause? Does it flatten out at 3? No, it's going up, right, at a rate of change of 12. It's heading up. But what happens? What's significant there? So is it a rest stop? No, because a rest stop has a pause. A rest stop flattens out and has a pause. This isn't pausing. It's heading up at a rate of change of 12. It's just that where that second derivative is 0, it's changing from concave up to concave down. And that's called an inflection point. So the rate of change is 12, but the second derivative is 0. So what? The first derivative is pausing, right? So if the second derivative is 0, the first derivative is pausing. The first derivative was increasing, so we concave up. And then the second derivative 0 means the first derivative pauses, and then the first derivative starts to decrease. So at that moment, the first derivative is not changing, and that's why the second derivative is 0. So you get a pause in the first derivative because its derivative is 0. So that's called, so when the rate pauses, it's called an inflection point. The concavity changes. So in this case, it's changing from concave up, or an increasing rate, to concave down, or a decreasing rate. Okay, anybody have a question on that? Yeah. Yes, right, where the second derivative is 0 is an inflection point. A rest stop is a special type of inflection point because the rate's pausing, but also the function is pausing. It's both. But this is not a rest stop. It's an inflection point where the rate of change is positive. Other questions? Yeah?
Is this graph no idea of x?
It was just a general version. It may be wrong. So what is the value of j? What is j of 3? Just enough to have the conversation. So, but it may be wrong. So in terms of the y values, I may be in the wrong place. Yeah, but it was just to have that conversation about the inflection point. So kind of. The shape is right, but yeah. Go ahead.
You said that because it says f double prime.
What's that?
Where it says f double prime.
Oh, j. Sorry, j.
That's why.
Sorry, my fault. J double prime. Yeah. Okay, does that clear it up? Sorry about that. Okay. Other questions? Last chance. Okay, so the next section is going to be optimization. So just a brief introduction here. So we know that with a function, what's the idea of a function? You can choose values of the independent quantity. And the function tells you what the value of another quantity is, or the dependent quantity, right? So f of x1 is a representation of the value of the dependent quantity, and the independent is x1. So optimization is about this. It's about, so we want to find the best, quote unquote, best value of the dependent variable. And so then the question is, so which value of the independent variable should be chosen to get that best value of the dependent variable? Okay, so we need to know three really important things. The first and most important thing is we need this function f, right? So we've got to have some function for which the dependent variable is what we're interested in optimizing, getting the best value of. So the function f, the dependent variable, is the one to be optimized. Second thing we'll need to know is what do we mean by best value? So there's two possibilities. We could want the largest value of the function, or we could want the minimum value. Sometimes, in terms of cost, minimum is better for cost. And then third, for that function, we'll need to know what values of the independent variable make sense. So what's the applicable domain? What is the applicable domain? So maybe not all x values make sense in the context. So we need just the part of the domain that's applicable to the situation. Okay, and so optimization, we're going to have lots of word problems, okay, especially over the weekend. These optimization problems are like real-world problems. And then after that, we're going to do what's called related rate problems, and those involve lots of real-world situations and like word problems. So I just want to talk briefly about approaching those. So the tendency for lots of students when you come to these problems is just try to find one that's similar. Try to find one that's similar, find the solution to that one, and then just kind of mimic a similar problem. And rather, your approach should be to orient yourself to the problem first. Ask yourself what's going on. So lots of research has been done with students and problem solving. And by far, students who succeed at these are students who start by understanding the situation rather than just trying to find a problem to mimic. And here's another one just like it, and I'm going to try to just change the numbers. Okay? That is kind of not a good recipe. So I just want to give you some suggestions suggested approach for whenever you have a word problem. Okay? In terms of orienting yourself to the problem first. And the first thing is to ask yourself, what's going on in this situation? What is the situation? And then what's the goal? Draw a picture if you can. Okay? This step should often take in terms of the orientation process to the problem, this step can often take the longest amount of time. Understand what's going on in the problem. Okay? Then the next thing is, we want to get focused on the quantities. And by quantities, I'm not talking about the numbers. I mean, those are representations of quantities, but by quantities, I mean like distance, velocity, volume, weight, temperature, etc. So what are the important quantities involved in the problem? That's key. And then the third thing is, which are changing, which quantities are changing and which are constant, and then which ones change together. So as you change one, what's going to change along with it because you changed the first one? So a big chunk of what we do in the rest of the course is going to be involving application word problems. And we really highly recommend that you start off by trying to understand the situation rather than just digging in or jumping in to solving it by comparing it to something else, another problem that's kind of like it. So really understand what's the problem that you're trying to solve. This is going to help you succeed at these. Okay, so remember your extension for web work tonight, and then we're not going to do quiz Thursday. It'll be another homework assignment for Thursday. Okay? See you then.